Hello chemistry students, Dr. Tellis here. We are moving on to section 6, looking at the function of a catalyst and its effects on the activation energy of a reaction, understanding the lock and key and induced fit models for substrates binding to enzymes, and we will understand the basics of the Michaelis-Menten model of enzyme kinetics. A catalyst is a substance that speeds up the rate of a chemical reaction. Their function is to provide a different pathway with a lower activation energy for the reaction. It proceeds by a different mechanism, meaning an alternative pathway. Catalysts are not consumed in chemical reactions, but is involved in the reaction at the particulate level. The overall stoichiometry for the reaction is unchanged. The delta H for the reaction is unchanged. Although a catalyst increases the rate of a chemical reaction, it does not influence whether a reaction is product favored or reactant favored at equilibrium. A catalyst simply enables a reaction to reach equilibrium more quickly. We looked at, let's say, an endothermic reaction where my delta H is positive, and a catalyst simply allows it to get there easier. It's a different pathway. Instead of having a high activation energy to get to the products, it has a lower activation energy. This would be with a catalyst. We could do the same with an exothermic reaction. If I have a big activation energy to get to my products down here, a catalyst would allow me to do it a different pathway with a lower activation energy. Here is a picture right here. This is my profile with my uncatalyzed reaction, with my activation energy being 264 kilojoules per mole. And we can see here with a catalyst, it's taking a different pathway, and it shows that the activation energy is lower. The delta H is still unchanged. The difference between my starting, my reactants energy, and my products energy, this delta H does not change, but the activation energy changes and the mechanism changes. Here is another example. We can see our catalyzed reaction, a lower activation energy compared to the activation energy of the uncatalyzed reaction. Let's look at enzymes. Most reactions required for life occur too slowly on their own, so organisms have developed biological catalysts to speed them up to the appropriate levels. These biological catalysts are called enzymes, which are typically large proteins. Enzyme catalyzed reactions are often 10 to the 7th to 10 to the 14th times faster than uncatalyzed reactions. For an enzyme to catalyze a reaction, several key steps must occur. The reactant, the substrate, must bind to the enzyme. The chemical reaction must take place there, and the products of the reaction must leave the enzyme so that more substrate can bind and the process can be repeated. The location in the enzyme where the substrate binds and the reaction occurs is called the active site. The active site often consists of a cavity or a cleft in the structure of the enzyme into which the substrate or part of the substrate can fit in just in the right orientation so that specific bonds can be broken and or made. We have two different examples here, two different models. In the lock and key model, the enzyme's active site is pictured as being a rigid structure that is complementary to the shape of the substrate. The shape of the substrate is pictured as fitting into the enzyme's active site precisely like a key, or the substrate, fits into a lock, and the lock being the enzyme. We can see here our substrate, this is our lock and key model. Our substrate has 3 little jagged points here, and here is our enzyme with the 3 little jagged indents, and it fits just like a lock and a key. See how beautifully it fits. But we also have this induced fit model. The enzyme structure is viewed as flexible, so that upon binding of the substrate, it changes to fit the substrate. So the substrate goes down into where the active site is of the enzyme, and we can see here that it changes to become complementary to the substrate. Like we said, enzymes have enormous catalytic activity. And like we already said, the substance whose reaction the enzyme catalyzes is called the substrate. This is the substrate that is going to the active site of the enzyme. The formation of the enzyme substrate complex provides a new pathway to products with that lower activation energy. And we can see here's where it binds and it forms that complex. And then we have two different products formed. Now let's look at the Michaelis-Menten model of enzyme kinetics. At low substrate concentrations, the rate law of the reaction is often first order in the substrate. At high substrate concentrations, however, the rate of the reaction levels off and the rate law is zero order in the substrate. The Michaelis-Menten proposed a general theory of enzyme action based on these kinetic observations. They assumed that the substrate and the enzyme formed a complex, ES, and the chemical reaction then occurs and the enzyme and the product are released. So we have the enzyme plus the substrate forming this complex. And then the complex, we can see, produces the product and the enzyme. And we can look at this and remember, if I'm looking at my overall product, if I have the same substance on the right side of the arrow and the left side of the arrow, that they cancel out. So that ES will cancel, the enzyme will cancel, and I'm left with my substrate producing a product. But it was essential in order for this reaction to happen to have that complex and to have the enzyme. Michaelis and Menten were further able to show that their mechanism led to the following equation for the rate or velocity of the reaction, V. They came up with this equation where V max is the maximum rate of the reaction, Km is a constant called the Michaelis constant, V is plotted versus S, there's my V max and my S, and this equation fits the curve right here well. Next, we're moving on to section 7. You're going to be able to understand the concept of a reaction mechanism and the relation of the mechanism to the overall stoichiometric equation for the reaction, describe the elementary steps of a mechanism and give their molecularity, identify reaction intermediates and elementary steps, and predict the rate law for a reaction given a simple mechanism and the identity of the rate determining step. Beyond simply telling us what factors influence the rate of a chemical reaction and how we might be able to speed up or slow down a particular reaction, chemical kinetics also gives us insight into how a chemical reaction actually occurs. The reaction mechanism for a chemical reaction is the sequence of bond making and bond breaking steps that occurs during the conversion of reactants to products. Based on the rate equation for a reaction and by applying chemical intuition, chemists can often make an educated guess about the mechanism for the reaction. In some reactions, the conversion of reactants to products happens in a single step, and that's envisioned as the logical mechanism. Most chemical reactions occur in a sequence of steps. Let's look at this one right here. Br2 plus 2 NO molecules to give me this product. A single-step reaction would require that 3 reactant molecules collide simultaneously in just the right orientation. 1 Br2 molecule and 2 NO molecules would have to collide at the same time and in the right orientation. The probability of this occurring is small, so it's reasonable to look for a mechanism that occurs in a series of steps, with each step involving only 1 or 2 molecules. Here's one possible mechanism. We take a Br2 molecule and an NO molecule. They might combine in an initial step to produce an intermediate species, a Br2NO. Then, this intermediate would then react with the second NO molecule. So we'd take our intermediate here, react with the second NO molecule to give us our 2 BRNOs. The equation for the overall reaction, we then take and add those 2 equations from the 2 steps. So we took a Br2 and an NO to get the intermediate. Brought the intermediate down and added the second NO to give us our product, our 2 BRNOs. The overall reaction should be the same as the previous slide. We have Br2 plus 2 NOs. And if we look, I'm going to draw a little line down our arrows. The Br2 NOs cancel. And notice I have 2 NOs right there, a Br2 right there, and my product right there. The probability of there being 2 steps over 1 is much greater. Now, collision theory takes us back to what happens at the molecular level. Rate is proportional to the number of collisions in a given period of time. But remember that not all collisions yield products. There could be a couple reasons for this. 2 things could collide, but they don't have enough energy to break apart those reactants. They also might not have the right orientation. They might not hit each other in the right fashion to make those products. Here's an example of O3 plus NO. This occurs in a single elementary step, but there has to be the right amount of activation energy and the correct geometry to take an O3 molecule, hit it with an NO molecule, and if it hits just right, one of those O molecules will break off and join the NO to create an NO2 and leave me with an O2. But like we said, most others involve a sequence of elementary steps. We add them together and we get our net reaction. Let's look at the decomposition of ozone in the stratosphere. I have O3, which is ozone, and in order to go from ozone to oxygen, we think might be a 2-step process. This first is a unimolecular, where I just have O3. I have one molecule of O3. Now, how is that breaking down if it doesn't have anything to collide with? Well, in a unimolecular reaction, the reactant species must acquire enough energy to break apart. Well, where does that energy come from? It can come from collisions of the reacting molecule with other molecules of the same kind. So an O3 molecule with another O3 molecule, with solvent molecules, or with some high energy background molecule. So when I take that O3, we think maybe it breaks down into an O2 and an O. We bring down that intermediate O, bombard it with an O3, and we get 2 O2s. Here's another example, a 3-step process to give us our overall reaction of 2 NH3s plus an OCl. Let's see how it goes about that. We take one NH3 with an OCl to get our intermediate here. Notice that I have NH2Cl and an OH minus. We bring down this intermediate, hit it with another NH3 to get N2H5 and chloride ion. Chloride ion is one of my products. We then bring this intermediate down and combine it with the OH from up there, and we get our 2 other products, N2H4 and H2O. All of these are bimolecular elementary step processes where I'm just hitting 2 molecules together. The rate equation for a reaction must be determined by experiment. It cannot be predicted from the overall stoichiometry, and this is true for every one of our rate laws that we've done. In contrast, the rate equation for any elementary step is defined by its reaction stoichiometry. The rate equation of an elementary step is given by the product of its rate constant and the concentrations of the reactants in that step. Let's look at this one. Our first elementary step, let's say I just started with A to make my product. It's unimolecular because I only have one reactant here. To make my rate equation, I would say the rate is equal to K times the concentration of A. Let's look here. I have A and B for an elementary step colliding to make my product. So it's bimolecular. So I'm going to say my rate is equal to K times the concentration of A, concentration of B. Here I've got 2 A's bombarding. It's bimolecular, so I'm going to say that's concentration of A squared because there's 2 A's. 2A plus B, so that's a termolecular. 1, 2, 3. So I would say A squared times B. So looking back at my ozone decomposition, my first step was unimolecular. We said O3 breaking down into O2 and an O. So my rate for that unimolecular step would just be the rate is equal to K times the concentration of O3 because that was my reactant. For step 2, that was bimolecular, I'm going to have rate is equal to K, and we'll just call that K prime. Concentration of O3 times the concentration of O. Again, the K and the K prime are not expected to have the same value because both of those steps have different molecularities, unimolecular, bimolecular. Let's look at this example. Hypochlorite ion undergoes self-oxidation reduction to give chlorate and chloride ions. We think the reaction is going to occur in 2 steps, step 1 and step 2. What is the molecularity of each step? Write the rate equation for each elementary step. Show that the sum of these reactions gives the equation for the net reaction. See if you can set that up. For this first one, I would have the rate is equal to K times the concentration of ClO minus times the concentration of ClO minus, which you could then reduce or simplify it and say rate is equal to K times the concentration of ClO minus squared. And for the second one, ClO2 minus times the concentration of ClO minus to give us the rate of that second step. And when I combine the two together, notice that the ClO2 minus is on both sides. Nothing else is going to cancel. I'm going to have ClO minus, ClO minus, ClO minus. So I have 3 ClO minuses, creating my chloride, so 2 chlorides, and a ClO3 minus. Both of my elementary steps were bimolecular, and the sum of both of those steps should be the same as this that I started with. Try this one. Nitrogen monoxide is reduced by hydrogen to give nitrogen and water. One possible mechanism for this reaction involves the following reactions. What is the molecularity of each of the 3 steps? What is the rate equation for the third step? Identify the intermediates in this reaction. How many different intermediates are there? Show that the sum of these elementary steps gives the equation for the overall reaction. Pause the video here. First of all, the molecularity of each step. I have 2 NOs, so this is bimolecular. 1 and 1, so that's bimolecular. 1 and 1, that's bimolecular. Each of the 3 steps are bimolecular. The rate equation for the third step, 1, 2, 3. I would say that rate is equal to K times the concentration of N2O times the concentration of H2. That would be for the third step. It wants to identify the intermediates in this reaction. Well, one intermediate would be this N2O2, and the other intermediate would be N2O, N2O. We know that because those are not seen in the overall equation, and because they're on the left and the right side, they cancel out. Those are intermediates. Now let's show that the sum of these elementary steps gives us our overall reaction. So I'm going to put a line down here. When we cancel out those intermediates and bring down everything else, I'm going to bring down my 2 NOs to give me the 2NO. Bring down my 2 H2s to get 2 H2. And on the right side, I have a 1 H2O and a second H2O and an N2. And that gives me my overall sum of those elementary steps to get my overall reaction.